Time to revise, reach for the skies, put in the work, success, no surprise. Ask no questions, I tell no lies. Let's kill the exams, 2025.
I've had training.
The training is nothing. The will is everything. The will to act.
Yield.
This time for
Chemistry.
Yeah, baby.
Hello, hello, hello. Welcome to Let's Get to the Marks. Let's go, let's go, let's go. What we doing? What we doing? Where am I? What's happening? Oh my gosh. Arrhenius equation. Oh my days, not the Arrhenius equation. Where are we? Okay. Hello guys. Yes, going through something called the Arrhenius equation today. This is part of the rates of reaction topic. It's part of, depending on what exam board you do, you've got to cover this beast. And this is just a small part of rates of reaction. I'm not going over the whole of rates of reaction. I will do the rest of rates of reaction in another lesson, but like 2 or 3 people asked for the Arrhenius equation, and you know, that's half my viewer base. So we're going to go through the Arrhenius equation. So what's that all about? Well, here's the equation. K equals AE minus EA over RT. We're going to work through a whole bunch of exam questions in all the different scenarios that they can possibly ask you that will come up in your exam. And yeah, what can we say about the old Arrhenius equation? Well, if you look up the word heinous in the dictionary, wrongful act, a crime, utterly odious or wicked, monstrous, disgraceful, evil, and you could describe all those things when you're thinking about the Arrhenius equation. However, just for some context, you don't need to know if you're A-level, you'll never be asked about this, but just for some context, you put your makeup on and you got an expiry date on your MAC makeup or whatever, like a 2-year expiry date. That's all thanks to this Swedish dude down here. This is Svante Arrhenius, who came up with this equation, and this equation helps people in industry predict when things are going to expire. So like those medicines in your medical cabinet, paracetamol, aspirin, you'll see there's an expiry date on them. It says EXP and a date. How do they know when these are going to go off? Well, his equation takes into account the rate constant at a specific temperature, so they know store these in a cupboard at room temperature, and this is when they'll go off. Over time, your makeup, your medicine, and your stored food starts to degrade due to chemical reactions, and so that's how the Arrhenius helps us. It's basically an industrial an equation used to this day in industry, even though this dude came up with it back in the 1880s or whenever he came up with it. He won the Nobel Prize as well, but that was for some other stuff. He did panspermia and various other weird and wonderful things. Right, let's check out this equation. So this is the one they give you in all of your exam boards. K equals AE minus EA over RT. Now I prefer this to use like this, which is the natural log of K is equal to the natural log of A minus EA over RT. So I prefer that application, and so I would memorize this one myself. This is what I would memorize. Some people prefer to memorize that. They normally give you the Arrhenius equation. Sometimes they don't, so we're going to look at examples of where they give it to you and where they don't. You do need to know what all of these things mean. So K is the rate constant, EA is the activation energy, T temperature is measured in Kelvin. Now check this R, this is the gas constant 8.31. This is measured in joules, just like the activation energy there, and also Kelvin. So one thing we have to be aware of is when we come to dividing activation energy by R, we have to make sure they're both in joules, and that's something that you have to look out for. That's one of the top tips with the Arrhenius equation. And then A doesn't have a unit. Okay, let's zing on. So these are the top tips. If I had to revise the Arrhenius equation and just remember a few things, what I would be remembering is I'd be trying to remember my top tips would be for this equation is just to remember that there's a conversion between kilojoules and joules that you're going to have to make, and also just that activation energy is always positive because you're putting the minimum energy in to break bonds, and so that is positive, not negative. All right, all right, all right, all right, 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 right. Let's zing on and get on with this bad boy stuff. Okay, let me just do a quick mic checkle. Um, mic check. Hold on, turn my volume up, then I can tell. Nope, I can't hear Jack, and can't hear nothing. Okay, let's try. Oh yes, yes. All good, all good, all good, all good. Just have to do a quick check now. Right, let's get on and do some of these. So let's go. I'll probably make a pack of all of these as well. So now I think I will shrink this down a little. There you go, so everything fits. Right, a slow reaction has a rate constant K. You're going to need a scientific calculator if you want to take part in the live. Really, if you want to actively do this Arrhenius equation. So I've got a whole bunch of questions to work through purely on the Arrhenius equation so that you can be an expert at the end of it. Right, slow reaction, rate constant K, 6.51 times 10 to the minus 3 mole, minus 1 dm3 at 300 Kelvin. Use the equation natural log K equals natural log A minus EA over RT to calculate a value in kilojoule per mole for the activation energy for this reaction. The constant A is 2.57 times 10 to the 10 mole per decimeter, and the gas constant R is 8.31 joule Kelvin mole. So what we want to do here is smash all the numbers in, rearrange, and see if we can work out the answer. So let's go ahead and do that. And what we're going to do, we're going to go through. There's three main styles. There's two main ways that they ask about the Arrhenius equation. Some of them are just like this, which is just bare straightforward, plug the numbers in. We're going to go through that. And then there is using the graph. And so those are the two main styles. They'll either ask you for one of the variables, like so here they want the activation energy, so they want that variable EA, and you just got to plug all your other variables in, rearrange the equation and come up with the answer essentially. And you just have to remember that there's a conversion that you need to do with activation energy, and you'll always have to do that conversion, or near enough always have to do that conversion. So there's slight variations on it, but that's pretty much what you got to do. And then there's the graph ones, which we'll look at too. Okay, so and once you're an expert on those two, whenever you see the Arrhenius equation, it'll just be 3 marks basically. Easy peasy. Okay, so we've got this natural log K equals natural log A minus EA over RT. We want to rearrange that to find EA. Oh my good gosh. So what we can do, we can do link A. Hold on peeps. Let's see if we can rearrange this. Equals minus EA over RT. So what we might want to do is go ahead, smash that in and see if you can come up with what is the natural log of K, which is 6.51 times 10 to the minus 3, take away the natural log of A, which is 2.57 times 10 to the 10. Let's go ahead and do that and work that bit out first, and then put that as equals minus EA over RT. So that's the starting point. I've just subtracted natural log of A from natural log of K. Let's go ahead and bust that out. So what have I got? Oh my days. So I got, like, I've done K, and you probably can't see that. I've got minus 5.03. Now what I want to do is I want to take away from that the natural log of A, which is 2.57 times 10 to the 10, close bracket. What have we got? We've got an error because I've flopped. Oh my gosh. Any problem with doing all of this? Not sure about that. Minus 18.93. Anyone else got that on their calculator? Anyone work that out? So what we're trying to do here is ln 6.57 times 10 to the minus 3, and then let's take away ln 2.57 times 10 to the 10. That is some beautiful writing. Absolutely bellissimo. Okay, let's try that again. I think I got 18.939, but let's just try that again. So I'm going to go, always got to double check on these with my fat fingers and not pressing the wrong thing. Okay, yeah, more or less 5.03. Take away. Oh, I got minus 28.9. Okay, minus 29 I got. So, don't know if anyone else got that. Minus 29.99. I'll soon know if it's incorrect. Sounds like it could be well correct for that. And then what we've got to do, that is equal to minus EA over RT. So I'm going to want to do minus 29.99. I got minus 18.93 the first time I did it, but and then I'm going to times that by R and T. So times 8.31 times 300, and that is going to equal my minus EA. Now, don't worry about the minus sign. Whenever you get activation energy, I'm not bothered what comes out in my calculator. It's going to be positive. It's endothermic because you're breaking bonds with activation energy. So let me just see if this works out right. Maybe I've done the old that bit wrong. Let's see. No, it sounds about right. I got 72,000 minus 72,284. As I said, I'm not bothered. So I got minus 72,284.5307. I'm actually not fussed about the minus sign because I know that's going to be positive, blah, 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 blah. So I'm going to round that up. Look, that is bigger than that. Whatever, 72 whatever thousand that is. But actually, one little step, I did warn up before, we've calculated this in joules. What did they want the activation energy? They always want it, look, in kilojoules per mole. So I'm going to need to divide by 1,000. So I'm going to do 72,284. I'm going to divide that by 1,000. And that is going to give me 70, oh my days, 72. Now you might get something slightly different. I don't know what I'm writing there. It's all going a bit pear-shaped. Now the 8's bigger, so I'm going to round that to 72.3 kJ. And that is the correct answer. Luckily, I already know that. So, wunderbar. Yeah, so that is the activation energy. Now that looks some scrappy, messy writing, but there we go. Okay, so those are quite straightforward. You just got to get used to handling those numbers. And like I say, practice makes perfect. So I'm going to do a whole pack of every single Arrhenius equation that I'm going to release on my channel at some point. I'm going to go through all the calculations with every single one that they've done for AQA, OCR and that. Just a big fat pack of Arrhenius questions. But as you work through and you practice and practice, you'll start to spot where you make a mistake. Notice I had to do ln K minus ln A about 3 times to get the correct answer. I don't know why I got minus 18.93. I don't know. Didn't put the bracket in the right place or whatever. So it's one of those you start spotting where you normally might go wrong. Anywho, any questions about that? Let's move on. Let's do another one. Let's bust out another. Well, okay. So this time we've still got the Arrhenius equation. I don't like this version. Okay. I like to use, you can use that version of the Arrhenius equation. I like to use this version. So I would memorize myself this version because I prefer this version. Natural log of K equals natural log of A. What have I got? Minus EA. Oh my god, I can't even remember the rearrangement. What is it? Plus minus EA over RT. Okay. So I prefer that one. And then what I do with this, I just take ln A away if I need to. Okay. Let's move on. So what is this question about? Right, they've told us activation energy once again is in kilojoule per mole. This time they're not asking for the activation energy. They've given us the A, the Arrhenius constant. They want temperature. So essentially, they just want us to work out T. So how are we going to rearrange this to work out T? This looks like it might have a fiendish rearrangement. So what can I say? Let's have a go at this one. Yeah, lovely. These ones are normally a little bit more straightforward.
Stick around.
I'm gonna have to science the shit out of this.
it's not my birthday. Why is happy birthday written down? Oh, someone's birthday. Never mind. Whatever. Ho hum. Right, let's go, let's go, let's go. What is that? Please excuse my... Oh my god. Please excuse what? Aha. Oh yeah, don't forget, there's only a couple of people in here. I know. Well, see if you can hit the like, guys.
If you push the button,
Would you like it?
Like.
Okay, yeah, if you hit the like, massively helps out. I don't know what the connection's like today. Might be a bit pants. Right, let's go through this question. So, we want to rearrange this. So, I think I want to get T on its own. And it's just a case of putting all your numbers in and getting T on its own. So, I'm going to start again. I'm going to do ln K. I'm going to take away the natural log of A, ln A. I like to call it ln, I don't know why, but there we go. Take away the natural log of A, and that is going to equal minus EA over RT. This is the bit where I flop. So I'm going to try and do that, and hopefully... what have I done with my old scientific calculator? Oh my days. I've only been sitting here 2 minutes. Okay, let's see if we can work this one out. Let's type this, because this will be a brute if I write it. So we want to do, I want to do natural log. Let's do natural log. What's K? I don't know why that keeps coming out as capitals. Never mind. 2.48 times 10 to the 8. Yes. Minus 1 times 10 to the 12. ln 1 times 10. Oh my gosh. Okay. Whoopsie. I think that's supposed to be times 10 to the minus 8. How did that one come out like that? Okay. Times 10 to the minus 8. Alright. That looks grim the way I've typed that out like that. That looks absolutely disgusting. See if you can put that in your calculator and you can work out what that is. If you can, and you slap it on the chat, that would be very helpful. So I'm going to go... So that, yeah, because, you know, otherwise I'm relying on me to not screw up. The more people there is, the better. So I got minus 17.5 for the natural log of 2.48 times 10 to the minus 8. Let me just check. Have I put that? Ah! It's not to the minus 8. Oh my gosh. See what happens if you rely on me? It's all going to go Pete Tong. So it's not to the minus 8. So,
Whenever I'm about to do something, I think, would an idiot do that? And if they would, I do not do that thing.
And it makes a big fat difference, doesn't it? You get 19.32. So apparently, that's 19.32. And now I want to take away the natural log of 1 times 10 to the 12. Hopefully I'm not flopping on that one as well. All right. Take away. Okay. And if I do that, I get... yeah, I didn't even work that one out individually, but I get like 8.30. I guess I could round that to 8.31. I get like 8.302. I get minus 8.302. What was the natural log of 1 times 10 to the 12? So natural log 1 times 10 to the 12. So 27 point, I got like 27.63 for that. Something like that, and that equals that. So now I know I've got minus 8.302, and that is equal to minus EA over RT. So that is equal to minus EA over RT. And so what we need to do now is we want to isolate T on its little lonesome. So we're going to rearrange this bad boy. And what we're going to do is... what is minus EA? Now, minus EA is in 34.5 kilojoule per mole. I need to turn that into joules. You can't divide kilojoules by R, which is in J, just joules. you've got to put them in the same unit. So that is 34,500. So what I really want to do is rewrite this out. I don't really want to do any of it, but what am I going to do? 34,500. And then R is 8.31. This bad boy is R. So that is 8.31. So we're going to do that. And that is times T. So now I can just rearrange this. And we can find out what T is. So let's work out what T is, folks. If you beat me to it, feel free to 8.31. Oh, Sugar Ray Leonard. Do 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 do. Right, what is that? Then I want to go 3, 4, 500 divided by answer equals. So essentially, what you want to do is go 3, 4, 500. You rearrange that. I don't know. I got minus that times 8.31. That's 8.302. Might be a bit more accurate if I stick that in. Oh, it's looking ugly. And that is going to equal the temperature. So I don't know if anyone's managed to work that out. But if you do that and slap that in the calculator, 34,005. What is 8.302 times 8.31? You're going to find it's like 68.98. So I'm going to get like 3, 4, 500. If you're breaking it down, that's going to be over like 68.98. I might not get exact here going on. And that is going to be, I got 500.075, something like that. 500 point. Again, if I kept all my working in, it might be better, but we're going to put 500k there, and that is the correct answer. So, bish bash bosh. Yeah. You get 3 marks for that, and what can I say? It's just rearranging the equation. It's not that easy, but with practice, you do tons and tons of these, you'll become a bit of an expert at rearranging this equation and slamming the numbers in, and you'll get used to working out different things. So, anybody got any questions about that? Or we can go on to some of the harder stuff. Okay. Let's zip on to... What we got here? Blah, blah, blah. Oh, I can do that. Oh, this is a 5 marker. Okay, this is a 5 mark. I might come back to this one. This is quite simple as well. This is just smashing everything in. You just got to know your PEMDAS. Make sure you you carry out all of these beforehand. So make sure you just follow the rules. But yeah, essentially... Oh, sod it, let's do it. Should we do it? Should we go onto a graph? Don't want to make this a long one tonight. Shall I do this one? It's 5 marks. You just got to slap the numbers in, really. And so ln times, you just want to do that divided by that, and then the natural log of it. And then we want to do that, and that, oh, come on in, let's do it. Okay, let's do it. All right, folks, let me go to my thing. Give me 1 second. What I need to do.
Let's work the problem, people. Let's not make things worse by guessing.
Okay. Right. Let me go through. So you might want to bust along at the same time with your calculator. So what are we going to do? We're going to do ln K1 over... So what is K1? K1 is 1.55. That is times 10 to the minus 5. I'm going to divide that. Remember, you're going to do parentheses, whatever. You're going to do your brackets first. So you want to handle that before you natural log it. So you might be going like, oh, do I press natural log first? And then you're better off dividing these first, because what's in the brackets you should do first. So let's do that first. Then we can do the natural log of it. So let's go 1.55 times 10 to the minus 5 divided by 1.7 times 10 to the minus 4. Hopefully we get this right. 0.091, something like that. So you're going to have Lin 0.091. Oh my days, extra naught there. I'm going to work that out now. So got minus 2.39. So now I know that this here is minus 2.39. I had to carry those. You carry that out first, then you do the natural log. So you're going to end up with minus 2.39. That is going to be equal to minus EA over R multiplied by T. But this time our temperature is a little funky, so we want to sort this out inside the brackets first. So 1 over T2 take away 1 over T1. So we want to get that down into 1 unit, and again you want to do that first. So I'm going to do 1 over T2, and we do the minusing after. So yeah, let's do that. So what are we going to do? 1 divided by 333. Oh my good gosh. So I'm doing what's in the brackets first, folks. It's something along those lines. And that's because I've done 1 over 333. You can see the temperatures there. And then I want to take that away from 1 over 303. So take, let me do that. 1 divided by 303 equals, and that is going to equal like 1 over 303 is going to equal 0. I don't really need that number. Let's get rid of that. Make this super messy. 0.0033. Now, roughly, you should keep all of this business in your calculator. So it's going to be 0.003 take away 0.0033, and that is going to give me oh geez, have I done that correctly? Let's just bust that out again. That should give me minus 0.0003, and that is that there. So then I'm going to be left with, if I write this all out, oh my days, this is super long, isn't it? But it is 5 marks, so I guess I'm allowed 5 minutes on it. I'm taking a bit longer because I'm writing like a proper twit. And then I've got, that is multiplied by minus 0.0003. Oh my days. Okay. That doesn't sound right. I've buggered that there, haven't I? 3 times 10 to the minus 4. I think this should be a bit more accurate, and this is going to make my result slightly out because I didn't write 0.003000321, whatever it was. So it's going to make my result slightly out from the textbook answer, but let's go. Let's run with it. Let's run with it. Okay, so we need to rearrange this, and I want to make, what are we actually calculating here? Ooh, we're calculating the activation energy in kilojoule per mole. Okay, so what am I going to do? I am going to multiply both sides by R and then divide both sides by 0.003. So I want to get the R over here with the minus 2.39. So I'm going to multiply both sides by R, so minus 2.39 times 8.31, which is R. And then I want to get rid of that, so I'm going to divide both sides by minus, oh my days, minus 0.0003. And so what I'm doing is I'm leaving EA on its own by timesing both sides by R as that's been divided. I will remove that from there, cancel that, and the R will come over there. And then I am dividing both sides by 0.003. And then we're just going to smash that in the calculator, and that is going to give me my EA. So let's check out what that works out as. I'm going to times that by 8.31. Get 19.86, and then I'm going to divide that by minus 0.0003, and that is going to give me 66,203. That don't sound right to me, but what am I going to say? I've not used the right numbers, so it's going to come slightly out. It sounds okay, but remember that is in joules. When you calculate the EA, it's going to be in joules, but the answer is going to want it in kilojoules. And again, if they give you EA in the stem of the question and you're calculating A or T, they'll give you it in kilojoules, and you'll need to convert to joules to use in the calculation. So I do need to divide that by 1,000, and it's probably going to be in the correct range for the answer, but maybe not. 66.2 kilojoules is the activation energy. Now, actually, if I'd left these numbers incorrectly, where I went wrong is slightly here. If I left these numbers incorrectly over here, and if my fat head wasn't in the way of 1 over T2 minus 1 over 1, 1, when I did that, I didn't leave the numbers incorrectly. If I'd left them incorrectly, I would have got like 2.97 times 10 to the minus 4, and that would have made a big difference. If I divide this by 2 point whatever, I'd get closer to the true value. The true answer was 66.8, but that's what happens when you miss a few bits and pieces out. Right, what we're going to do... Oh, what's that? I don't want to know about that. Okay, yeah, no problems. So, yeah, this should be totally fine. I will make a little video on it as well where... See, when I do a live, I can't go through smoothly. When I do a video on it, I can get rid of... Well, I don't even get rid of all my... when I'm doing my videos, because it's just too long. But, yeah. Can be an improvement. Okay, so hopefully you will be able to have a go at those questions now when you get them, where you've got to put the numbers in. Rearrange it, like, just practice the same question. The problem is people might do one Arrhenius equation question when they do a past paper and then think, oh yeah, I'm all right at that. And then the next time they get an Arrhenius question in their exam, it's one of the other formats. And you're like, I couldn't do it. I'm rubbish at Arrhenius. No, there's only 2 or 3 different ways they ask it. We've just covered the ways where you've got to rearrange, but you probably need to do about 10 different ones of those till you become an expert. So you've just gone through 3 there. Now, 50% of the time, you're going to get a graph, and there is a method to these that you can apply every single time. So as baffling as this thing looks here, as baffling as this is, there is a method to this. And essentially, the method is that on an Arrhenius graph, Arrhenius, if you divide the y-axis by the x to find the gradient, y over x, which is essentially saying you're going to do ln k over 1 over t. If you do that, that is equal to minus EA over R. Now, this is something that you just have to know off by heart, and it's very, very important. And every single time they give you a graph, this is what you need to know. So the gradient on... I'm going to call it the Arrhenius graph. Arrhenius graph is equal to minus EA divided by R. Now, the temperature's been taken out of it. Oh, my God, that's just foul, man. The temperature has been taken out of this, right, because it's on the 1 over T and the ln K is gone. So, essentially, if you are asked to find the activation energy, which is what we're asked to find here. They want EA. Well, all I've got to do is find the gradient on this graph. And if I can find the gradient on this graph, then I know what minus EA over R is. And I just need to times by R and then convert to kilojoules, because this will be in joules. To use R and EA together, that's going to be joules over joules. I need to turn it into kilojoules at the end, my final answer. Divide by 1,000 and you got it. So you should have a go at this. Anyway, I'll go through and show you how to do. So what we're going to do, when you get these graphs, they're always a nice straight line. So what the hell is that? That is, oh, whatever. Let's draw a little triangle thing. We don't really need a triangle, do we? But we're going to do one anyway. So let's do it. Whee! So you could do it either way. It doesn't really matter. Oh, why didn't that? Oh, thank you. You straightened up. Right, so what I want to know is, this is my x, this is my y. I want to do y over x, and essentially y over x is equal to minus EA over R. Now that might be a bit hard. Oh, it's a bit hard with my fat face on the screen. Let's move my fat head, shrink me down. Actually, I'm just going to move my face down there for the moment. Excusez-moi. So what we need to do is now find these numbers. What we got, peeps. So, oh my gosh, I've got to work out what that is. 0.0012. That's 0.0013. So that's 0.00125. 0.00126, 127, 128, 129, 13. So that's 0.00128. I think, but my eyesight's bad. 0.00128. He says. And then I think if I come over here, oh yeah, we're all good. That's 0.001. Oh my gosh, 18. So I want to minus those, find the difference to find x. So let's smash that in the calculator. What is that? That's 0.0018. You might want to do this along with me. Minus 0.00128. I've now got, feel free to put up in the chat if I've flopped. So this is my x, 0.0052. Hopefully. So that's x. Remember, we're doing y over x. So my y is, what is that? Minus 2, minus 3, minus 2.8. I'm going with minus 2.8. So I think that's minus 2.8. Come down here is minus 14. Is that minus 14.1? That might be minus 14.1. Looks, oh, is it minus 14.2? I don't know. It looks like it might finish halfway in between this little square, and each one of these squares is worth 0.2, because look, minus 14, that there would be minus 15. 5 squares, so each one's worth 0.2. So maybe minus 14.1. Let's check that out. So if I go minus 14.1 and, oh, whoopsie, minus 14.1, take away 2.8. You get the idea, whatever I'm waffling about. I get 16.9. No, I don't get 16. What the arse am I on about? Oh, my days. Is 11.3. That sounds a bit better, doesn't it? Yeah. Okay. Starting to do... Anyway, the difference there. So it's 11.3 over that. Let's try this. 11.3 divided by 0.00052. Okay, I get 21. Now, I might be wrong. As I say, I do have the mark scheme somewhere on here. 21,730.769. That is going to be equal to minus EA over R. Think of it as like a speed distance. If you put that in a triangle, that would be minus EA at the top and these two at the bottom. So I need to times that. I want to get rid of the R. As the R is being divided, I'm going to times both sides by 8.31. That's going to get rid of the R. So I need to do 21,730.769, and I want to times that by 8.31. And that is going to equal my activation energy. But it's going to be my activation energy in joules, not kilojoules per mole. So you should know what we've got to do after that. So I got 180,582. 180,582. And that is joules. I want to divide that by 1,000 because this is supposed to be in kilojoules. In the equation, you'll always, when you work out EA, it will always be in joules. But they'll always give it to you in kilojoules. If you're not working out EA, they'll give you the activation energy in kilojoules. So you'll have to make the conversion by timesing by 1,000. But if you're finding the activation energy, and that's the variable they ask you to find, you always are going to get it in joules and need to divide it by 1,000. So it's very rare that they don't. So I got, I don't know, 180.58. Obviously, 3 sig fig at A level. So we're going to go with 180.6. Because the 8 is bigger than 5 or bigger, we're going to round that up to 180.6, and that's going to get you 3 marks. Now, that is the same every time you get a graph. Now, the graph questions have come up lots and lots of times, okay, at A level. So they've come up tons and tons of times, these graph questions. Oh, thank you. It is 4 significant figures. Well, yeah, maybe. How do you do significant figures? Is it what you discard any zeros from the left and over? Let's, yeah, I always get mixed up with significant figures. 181 would be 3. You're right. 181 would be 3. Absolutement. Yeah. I've gone to 1dp here then. 180.6. I'll leave it at that. I mean, you could leave it as 100. They haven't asked for you to round it, so 180.58 is going to be within the range on the mark scheme. If I could pull out the mark scheme, it will be within the range. But you're absolutely right. Important 45. Spot on. Okay, right. Look, they got enough of these questions, so I'll go for another graph question for you. This is a Fat 5 marker, but what you'll find is these are all they're all the same. So learning to rearrange is important, but the graph questions are actually the easiest because what you know, despite whether you understand any of this or what it's for, you don't need to. All you need to know is that the gradient, this is the most important thing on the Arrhenius graph. You can call it the Lin K1T graph, whatever. I'm just going to call it the Arrhenius graph. Gradient on the Arrhenius equal gradient of the straight line is equal to minus EA divided by R. And when you want to find, once you've worked out the gradient, you just times it by 8.31, which is R. And then you'll get the activation energy on its own. And then you divide by 1,000 and bish bash bosh, you've got all the marks. So you could try to do this with your calculator as I go through. I'm going to quickly plot this on. So what are these man asking me to do here? Oh my days. Okay, so we've got 2 missing values here. This has come up a couple of times if you're studying AQA to give it a missing value, 1 over T. Look, it's as easy as just going, if you want to fill that out, 1 over T, look, you just go 318. And then you practice. You use your exam technique. You go 1 over 313, and you'll see that that gives you 0.00319. So you practice it on a known example, and then you know what you've got to do. 1 divided by 318 equals 0.00314. Ah, it's time to move my fat head. Oh, on the previous question, I didn't move my fat head back out the way when we were doing this one, did I? No, this is the problem. I should have really thought, look, my face was over all the working. What a bell piece. Never mind. That was all the working I was doing, which obviously you could not see. So, yeah, what are you going to do? Hard floppage. Never mind. Right, back over here. So, what am I doing? 0.00314. And then here, this is just Lin K. So take K. Where's K? K, the rate constant K. And just do the natural log of 6.63 times 10 to the minus 7. So we're just going to do natural log 6.63 times 10 to the minus 7. And I did something wrong there. Okay, minus 14.22 is what I got. I probably should just leave it as minus 14.2 because they've done everything to 1 dp here. So I'm going to do to 1 dp. Okay, so minus 14.2. Now what they're saying is complete the table above. That was 2 fat marks. My God, that was a nice, easy 2 marks, right? Bash, bish. What we need to do now, they've given us the Arrhenius equation. We don't really need that. Use the data in the table to plot the graph. They're doing that to throw you off. You just need to know this. You don't actually have to use that here. Use the data in the table to plot a graph of Lin K against 1 over T. So we just need to put this. Now, here's a question. Do I start from 0? I don't need to. 13.6 is my lowest, and 17, basically I need to go up to 18, and I need to start from 13. So I need to go 1 below the lowest. So I'm going to start there at minus 13. That's going to be minus 14. Excuse the crustiness. That's minus 15. Minus 16. Minus 17. and I'm going to have minus 18, but I'm not going to need to go to minus 18. And then it's just a case of plotting your points on. So each one of these is worth 1. You can see there's 10 squares between each of these. So minus 17.7. We're going to want to be down somewhere like there on that line there. 3 from minus 18. And then what is it? 0.000341. And these are worth 1 each. So I'm going to come down here and go bish. Now, for the Arrhenius graph to work, you're going to get a straight line, okay? So if it's not a straight line, I know I've flopped and I need to pull out the rubber and redo. So there's the first one done. I've done that. Let me just mark that because I'll get myself in a twist. Minus 16.3, so I'm going to come to here and then zing along. Oh, it's right there. Okay, is that right? God, my eyesight, I'll end up doing something in the wrong place. Oh, my days. Look at the sensitivity there. Right, minus 14.9 is going to be here, just before 15. And minus 14.9 goes with 319. Oh, my days. We're all the way over here already. Okay. Yeah, looks straight line so far. And then we're on the second last one. So minus 14.2 is 318. So 318 is just 1 along. And what did I say? 14.2. So hold on. Minus 18. That doesn't look right. I flopped hard on something here. That's 3. Where am I? Minus 14.9. See, this is what happens. Minus 14.9 is on 19. That's okay. Minus 14.2, which is going to be here. And that is 314. Oh my gosh. You see how I nearly flopped on that? So 314, that's 310. So 4 is there. Oh my gosh. Nearly messed that up. But you see, because I know it's a straight line, if you start varying off, you know you've done something wrong. What I was doing is I was looking at minus 14.2 and then I was looking up there at that one for minus 14.9. Yeah, so you stare at screens too long, apparently. 13.6 minus 13.6 is here, and we are at 310, so bang on the money right there. And now all I need to do is draw a straight line through all those points. So I'm going to select, I don't know, purple. Love a bit of purple. There we go. And then we're just going to work the gradient out for this. Now, do I need to do all of this? Oh, that didn't work out quite straight enough. Go on. Yay! Where's my face here? How much of... Oh, my face is blocking the whole graph. Isn't that wunderbar? Wunderbar! I'm going to shrink myself down. Okay. Alright, I'm right at the bottom of the page. God knows what that's all about. But, okay. So, look. You're just going to do y. We just want to do y over x. Remember, this is a fat 5 marker, so you're going to get 5 marks for this. You might think, oh, this has taken me some time, but you're going to get 1 for the plots. So you're now on 3 marks. You've got 2 for this, filling out this table. Another 1. That was the long bit, plotting that, right? You've got at least a couple for that, maybe 1 or 2 for that. And then it's just a calculation of y over x equals EA over R. So you don't even really need your graph to do this next bit. So even if you flopped on the graph, you could work this out from this. Because look, you're just going to go... For our y-axis, we're just going to do minus 17.6 minus 13.6. That's y. So what is y going to equal? Y is equal to 17.7, sorry, take away 13.6. So that is 4.1. And I'm going to divide that by, let's check out, what have I got? 0.00341 minus 0.00310. So 0.00341 minus 0.00310. So I don't even really need the graph because I can do that. And that is going to give me 0.00031. Now, when you do these activation energies tend to be quite big. So that makes sense. 4.1 divided by, what is that? 3.1 times 10 to the minus 4. and I got 13,000. So what did I get from that? My gradient is equal to 13,225 0.8, and 13,225.8 is equal to minus EA divided by R. Well, I need to get rid of the R and leave EA on its own because that's the activation energy. Let's times that by 8.31. Oh my god. Oh my days, it's so long. And I get 109,906.45. Now, as I said, depending on all the little numbers you leave in your calculator or whether you're breaking it down as you go, you're going to get different answers. So what do I do now? You don't really need to draw the triangle important 452, but you could do. You should do, maybe, to show you working of how you worked out X and Y. But you don't really need to. You can do it from the table if they've given you a table of results. Sometimes they won't give you a table of results. They'll give you the straight line. Then you need to draw the triangle. Of course, what the number means, why do we calculate Kc? Kc is the equilibrium constant. And yeah, it's just a constant at a particular temperature. Does Arrhenius have two R's? So at a particular temperature, Kc will change with temperature, but not with anything else. But for every reaction, there'll be a particular Kc for that reaction at a particular temperature. It's called the equilibrium constant, and you find it by dividing the products by the concentration of the products by the concentration of the reactants, but you have to raise them to the power of the coefficient in the equation. So if I make 2 carbon dioxides, I times my concentration. Well, let's not do carbon dioxide. If I make 2 sodium hydroxide, 2 moles of sodium hydroxide in the equation, as in not moles, as in the coefficient is 2 in the equation, then you'll do the concentration of sodium hydroxide to the power of 2. But you're dividing the products by the reactants, and that will give you the equilibrium constant. And that is a number that is the same for that reaction always. It's constant at that temperature. But as soon as you change the temperature, you change the Kc. So, right, the final step here is this is in joules, and of course they've asked for kilojoule per mole. So I'm going to divide that by 1,000, and that is going to leave me with 109.9 kilojoule per mole. You're going to do products divided by reactants. No, you'll have the equation. So when you're given the equation, like, I don't know, H2SO4 plus NaOH, right? Sodium hydroxide plus sulfuric acid. Say you were doing that. I will divert. By the way, that's the correct answer for that. So that would get you all of the 5 fat marks. 2 marks for that. And then you would get those marks there. You just got to remember to divide by 1,000. Let me just show you. For the equilibrium constant, you're going to do products divided by the reactants. And remember, it's the products over the reactants. And that is going to give you Kc. Now, if we had sulfuric acid, and we neutralize that with sodium hydroxide, and I want to... Well, this is a bit crap because this would not set up an equilibrium. So this is totally made up and inappropriate because it would not set up an equilibrium, but never mooned. So I'm going to go Na2SO4, and I'm going to need to do plus H salt and water. Okay, this is not an equilibrium reaction, I do not believe. So this is completely made up, but it's just to show you what you've got to do. Now, obviously, that's not balanced. I'm going to need a fat 2 there. Do I need anything else? That's 2 H's, H2. Oh, I think I need a 2 here, right? Is that balanced now? How many of them have I got? I've got 1 of them, 1 of them, 2 of them, 2 of them, 2 H's there, 2 H's there, 4 H's there, Almost there. We're balanced. Okay, so if I was to write this, if they said give me the equilibrium expression for this reaction, it would be Kc is equal to the reactants over the products. So I want the concentration of this. Now, this would be my equilibrium expression. Obviously, I've not put the numbers in because we don't know the numbers as of this moment. We could make some numbers up if we really wanted to, some concentrations and stuff. And you would then go NaOH, and you'd look at the two in the balanced equation. So you need the balanced equation for these guys, and they'll give you that 90% of the time you will get the balanced equation. So that is your equilibrium expression. It's the products divided by the reactants. Don't forget, when doing these, you need to, obviously, before you times these bad boys together, you're going to need to do exponentials first. So you're going to need to square that first and square that first before you times it by that. Okay, and yeah, that's going to give you the Kc. Now, that will always be the same for this reaction at a particular temperature, but if you change the temperature, it will affect the value of Kc, depending on whether it's exothermic or endothermic, the Kc, the reaction and the Kc. But Kc will change with temperature. Now, this is not saying there's 2 moles. Remember, this is a coefficient. This is a coefficient. This is part of the balanced equation. That's not saying there's 2 moles. They will give you the concentrations, or you'll have to do the ICE. I have done a lesson on Kc. I've got a live out there on Kc. They'll give you the ICE, the initial, the change, and equilibria. And what you need to do is from that, you can work out all the values of the moles at equilibrium. Now, sometimes we can assume that the moles are equal to the concentration because they'll tell us we have 1 decimeter. So the moles are equal to the concentration. Other times they will give us a different volume, in which case you're going to be given the moles of the reactants and products, or you're going to have to work that out as a step in the kind of question, work out how many moles of each you have. Once you know the moles, you divide by volume, because of course this goes in hand with this, and that is moles over volume gives you the concentration, gives you C. So N over V gives you C. So you may well have to do N over V for each of these, and then square, and then you smash that in and you get that. And that'll be like 3 or 4 marks if you've got to do the ICE thing first. Anyway. Oh, volume. Okay, so why doesn't volume change Kc? Volume doesn't change Kc because volume won't change Kc. Concentration, changing the concentration won't change Kc because it's just the Kc is a ratio of the products over the reactants, and the ratio, although the amount may change, the at equilibrium, the ratio will end up equaling the same ratio, even if you've changed. So if you increase the concentration of those and decrease the concentration of those, or if you change the volume, the ratio will still be the same. Basically, if you change the volume, you're changing the volume for the ones on top and for the ones on the bottom. So you're dividing everything by the same volume. So you're going to end up with the same ratio. So that's why. But yeah, that was a bit of a long-winded explanation. But only temperature is going to affect the Kc. Catalysts affect the equilibrium position, but they're not going to change the Kc. Okay, so anyway, back just to finish off with the Arrhenius equation. Just a couple more things on this. So I'm just going to do a couple more on the Arrhenius, and then I'm going to finish up. So these will test you on the graph. So we've got a couple of multiple choices here for you guys. So this is where you're going to visualize. It's a multiple choice. You've got 60 seconds to do it. Oh my days. Or maybe 90 seconds on one like this. A graph is plotted of natural log of k against 1 over t. It's the Arrhenius graph. Always natural log of k against 1 over the temperature. K is the rate constant, temperature's in K. The gradient has a numerical value, so they're even giving us the gradient of minus 55,000. What is the activation energy in kilojoule per moles? So we have to visualize that we know this minus 55,000 is equal to, they haven't told us here, but this is the thing you've got to learn off by heart if you want to do the Arrhenius graph equations. You've got to know that. So whatever the gradient is equal to minus EA over R. R is always 8.31. They haven't given it to us here that it's 8.31, which is a bit cheeky. So what we're going to do, we're going to go minus 55,000 times R, which is 8.31, and that equals minus EA. So, and then, absolutement, we are going to have to divide, oh my days, oh my god, I can't even type properly, 55,000 times 8.31, what a, yeah, and you're going to get 457,050 as your activation energy. Remember, it's in joules, but we always express it. It's always the standardized into kilojoules. So with the EA, you're going to divide by 1,000 once you've calculated it. Every time you calculate the EA, it's going to be in joules. Divide by 1,000, and you're right. The answer is D. So there we go. And that's basically the same. Whenever you get these graph questions, you're going to end up plotting, doing a straight line, finding the gradient, times the gradient by 8.31. You get minus EA, divide by 1,000 to put it into kilojoules. However, if I've got the Arrhenius equation and I'm working out A, or I'm working out K, or I'm working out any other part of the Arrhenius equation, then my activation energy, I need it in joules, because I'm not allowed to take my joules here. This is joules, and this has to be joules. When they give you to work out a different variable, it's mostly activation energy, but when they give you one of the others, like work out K, work out A, work out T, they're going to give you EA in the stem of the question in kilojoule per mole, and you're going to have to times by 1,000, otherwise you can't divide by R. So just remember that. But most of the time, you're working out activation energy, it seems. Okay, enough whiffle waffle. See if you can do this one. Very, very similar, because exam boards love to ask the same things. Oh, look, my little tiny face is down the bottom of the screen. What a bell piece. Let me sort that out. Oh, my days. I've got to get different glasses, these non-reflective glasses. Okay, a graph of natural log of K against 1 over T. T in K for a reaction has a gradient with a numerical value of minus 4,420. What is the activation energy in kilojoule per mole for this reaction? We're just going to do the same thing, right? They're telling us, so see if you can work this out. They're telling us that this is equal to, that is the gradient, so it's equal to that. So guess what? Do the same thing. That times 8.31. And then we want to divide by 1,000. Awesome. The answer's C. Nice. So once you get hold of it, the Arrhenius equation won't intimidate you, because if you're given graphs, find that gradient, times by 8.31, divide by 1,000, boom, you've got it. So, and they do that all the time. Look, I'm not going to do this one, but look, here's another one. Calculate the activation energy. All we're going to do, this is a 636 marker, right? This is in the last couple of years. I don't know if this is the 2023 paper, but it was one of the recent papers, AQA. And all you've got to do here is obviously plot ln K here. You've got to find these. That's dead easy. 1 over T. You do 1 divided by 302. You get that answer there. Then you do, for this is ln 1 over T. So we just need to ln 3.7 times 10 to the minus 2. We get that. And then we're going to plot we're going to plot this onto here, and then literally you're going to end up with the same answer. You're going to end up with the same answer when you do this. You do the exact same thing. You find the gradient of the graph, times it by 8.31, divide by 1,000. I ain't going to go through that one now because it's going to be long. I'm going to finish with this last example. This time they want us to find the Arrhenius constant A for this reaction. It's worth 4 marks because you've got to do the units as well. So see if you can do this one. I will at some point, I don't know when, maybe after Christmas, I don't know. I'll put all these Arrhenius questions together in a neat, concise 1 hour pack. I might, like with loads of other questions from different exam boards. I have thrown a couple from other exam boards in. Yes, you got to remember that the gradient equals minus EA over. No, the gradient isn't minus EA over RT. It's EA over R. Yeah, you got it. You got it. Minus EA over R. So for this one, we don't need the gradient. So, and I don't like this. I don't like this. I don't use this. I always recommend learning this. Ln K equals ln A minus EA divided by RT. I prefer that equation. It's basically just a rearrangement of that to get rid of the exponential bit. You just natural log A and K. And so I prefer that. So all you're going to do is put the numbers in and rearrange to find A. I love the way I say, all you're going to do is do that. So see if you dudes can see if you can work that out. And you'll be an absolute hero if you can work that out. If you can work that out, you're a superstar. You'll definitely be. Okie dokie. I don't want to keep you guys long because everybody's got better things to be doing than doing the Arrhenius equation. So what we're going to do, 2.5 times 10 to the power 9. Let me just speed. Hold on. I feel the need. I feel the need for speed. Let's bust out. So the units are s to the minus 1. I'll just go through why that is. You are right. 2.57 times 10 to the minus 9. Oh, look, he's put his fat head on everything. So here's all the working out. Ta-da! Blue Peter made it earlier. That way. Yeah, that way. There. Okay. So you just got to arrange that. Bing, bang, bong. And then you'll get A. And then s to the minus 1 is the unit. Why is it s to the minus 1? Well, joules divided by joules cancels out. K minus 1 times K is basically K plus K minus 1. They cancel each other out. The joules cancel each other out. And then you're going to add S minus 1 because S minus 1 is our unit for the rate constant. So you end up with just S minus 1 as the unit. Anywho, that is one of those ones. What you did have to remember here, of course, oh my gosh. Some people find this bit hard. You got activation energy is 96.2. Remember, you cannot divide that. You can't put that over R without turning that into 96,200 joules because R is the gas constant and that's 8.31 and R is in joules per Kelvin. So we need to, so that these can be used in the same equation, we need to make sure that goes to joules. So they'll always do that to you just to mess with you. But once it's in this equation, you need to have turned that into joules. But yeah, they'll do that to mess with you. So just remember, it needs to go into joules in the equation. But if you're calculating activation energy, you're going to have to put it into kilojoules. So that's when you divide the final answer by 1,000. I think we're going to finish up there. And basically, we're going to finish up there on this one. Anyone got any other questions about chemistry? Someone wanted me to go through nomenclature, organic chemistry nomenclature. Like, yeah, I don't know if you guys love a bit of nomenclature. Like, how are you with your nomenclature? I will go through that at some point. I'm going to go through. I will do a lesson on nomenclature. I don't know how you dudes are with your naming. Because some of the naming gets really hard in chemistry. Some of it's dirty, easy, super duper easy. But like, I will go through naming at some point, and then someone else wanted me to go through how to do rates of reaction, but it depends how popular things are. Like, you know, like, I don't know if everybody wants to go through the same thing or whatever. Yes. So, where am I? No, I'm all over the chip shop. Chip shop. What the hell? Put my face over there. Let's move myself up here again. Boom. So, is anyone able to name that molecule? Yeah, phenol. So, phenol is when benzene is a side group, and you have to know the priorities. So, if you have a carboxylic acid attached to the ring, then it's going to become a side group. So it's going to become phenol. Or if you have like a hydroxy attached to the ring, it's going to become phenol. Because it's phenyl, it's become a side group. So when benzene is attached to a lot of things, it will become a side group. Alkyl groups are less important than benzene, so you would still be called benzene, like methyl benzene, ethyl benzene, 1,2-dimethylbenzene, that kind of thing. Yeah, I will go through nomenclature at some point. Look at this disgusting one. So what you do is you just count the longest chain. So 1, 2, 3, 4, 5, 6, 7. So it's heptane. Heptene, because we've got a double bond. And the alkene's going to take priority here. So we're going to go 1, 2, 3. So this is hept3-ene. And then I would need to name these two methyl groups. What's that? 5, 6. So if you were naming this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. So then you know the main chain is hept. I'm going to go 3-ene. And then I want my sides up here. I've got when you get a straight line like that, it's methyl. And you can see there on 5 to 6. So I'm going to call it 5, 6, di. That is supposed to say methyl, not squiggle, but I can't write. So 5, 6 dimethyl hept3-ene, basically. Hey. 5, 6 dimethyl. Branches go first. Yeah, the sides go first. Side groups go first. 5, 6 dimethyl hept3-ene. So we love a bit of naming. All right, let me give you. You said you're no good at arenes, or did you say benzenes? Well, you got. Okay. What about now? This is. Oh, Sugar Ray Leonard. Actually, I'm going to get off in a second because we've done Arrhenius. I'm now just waffling on about nomenclature. But some people have said they want to go over nomenclature. I'll probably do I'll do a whole lesson on nomenclature. So, well, watch out. If I don't put a ring in there, what do we call that if there's no ring inside? Or if I don't do this, some people do that for benzene. They put these in. They like to show it like that, a bit like the Kekule structure. That is just going to be a cycloalkane. So you'd count this up again and you'd go 1, 2, 3, 4, 5, 6. And then you'd need to know are amines or alkyls more important. Amines come above alkyls. There are various mnemonics for these, but they're pretty poor. Amines come above alkyl groups. So the amine is going to be part of the name, and this is just going to be cyclohexane is the main chain here. This is not a benzene ring. But I'm going to get rid of the final E, and I'm going to call this cyclohexanamine. I don't need to number it because the amine is the important one. So I'm going to call it 2-methyl. Oh my gosh, what the hell is that? It's the most dodgy M ever. 2-methyl cyclohexanamine. Yeah, naming's a bummer, but I should do a lesson. Maybe I'll do a lesson on naming. God, I'm losing the plot. All right, I should chip out. Yeah, cyclohexane. Yeah. All right, guys. I think I'm going to shoot off. Yeah. I don't know if people want me to do reaction rates next time, like where you've got to calculate the rate of reaction and the orders of reaction and all of that stuff and the experiments on initial rate, things like that. Or if they want me to do nomenclature, just leave a comment with whatever you would like me to do live on. I have had some people say nomenclature. Other people said reaction rates, but I did Arrhenius separate to the rest of rates of reaction. Arrhenius is right at the end of the reaction rate. The rest of the reaction rate is like how do you work out the rate constant or the rate equation and all of that business. So I could do the rate equation, or I could do nomenclature, or I could do any topic. It doesn't really matter. All right, nice one. Take care, guys, and thank you all. I'll see you again. Bye.
You're still here? It's over.